This next section is 5.2, and we want to work some problems here that address the circular motion concepts that we previously had up here. The pertinent equations are the centripetal force, centripetal acceleration is v squared divided by r, and thus the centripetal force is mass times that centripetal acceleration. These equations, of course, this equation you already know because it's Newton's second law, that force is mass times acceleration, but this is the new equation you must remember. We're going to look at balancing friction with centripetal forces for a car driving around a curve on a flat road. Well, if we have a flat road and there's a radius here, r, for the curve that the car is going on, a rudimentary car, and as it goes around, of course, it feels an outward force in this direction, which is going to be the mass of the car times the tangential velocity squared divided by the radius of the curve. And this will be the force that the car is experiencing in this direction. So the tires have to push inward with that equal and opposite force in the opposite direction, or toward the center, in order to balance the outside force and to keep it on the track as it goes smoothly around a circle. I've drawn this from the side. This would be the center of the circle, and of course this is a circle imagined in this direction. So if we have a car that has, well, let's say 2,000 pounds, that would be 1,000 kilograms. So we might have a force or mass of 1,000 kilograms. And we might have a velocity of 50 kilometers per second for the car, and a radius of 100, let's say to make it simple, a radius of this circle, which is 100 kilometers. Of course, that's not very much. That's pretty large. Maybe we ought to make it smaller than that. Let's make it 20 kilometers. That'll increase that some. Okay, now what force would we experience? The force we would experience would be 1,000, which is our mass of our car, times, remember, 50 squared. And that's kilometers. And so in our MKS system, this would be times 10 to the third. We can put 10 to the third, that'd be times 10 to the sixth, therefore. And we're going to divide it by 20, a radius of 20, times 10 to the third, because it's a kilometer. Kilo meaning 1,000. Here we have a kilometer squared, so it'd be 10 to the sixth. And if we work this out, we were going to have 1,02500 10 to the sixth over 20, 10 to the third. The 10 to the third cancels the 10 to the sixth, giving us a 10 to the third here. And 20 goes into 100 4 times. So this would be 40. This would be 40, I'll write over here, 40 times 2,500 times 10 to the third. So that would be equal to, let me move this paper up a little bit. That would give us 40 times 250, so 2,500, so that would be 0, 0, 0. That's 20, was 8, 9, 10, so that'd be 100,000 times 10 to the third. There'd be another third there, 4, 5, 3, 4, 5, 6, 7, 8. So our answer would be, the force would be 1e to the 8th, and that would be newtons. That'd be the force that'd be required to hold this car in place as it went around the corner. Now, I'll make this remark again. As I work problems explaining things, often, we can make simple mistakes. And so one of the things you want to do is always look at my notes and say, is there some simple arithmetic or calculational mistake here with something squared that should not have been, and so forth. And so normally I give extra credit for people who can find a mistake in any of my notes. Well, let me work this a little bit further now and say, what if we had not a flat road, but we had an angled road? And incidentally, this requires a lot of friction to hold this car in place too. So now what I want to do is take that same car, but I want to put it on an embankment. And so now, if it's on an embankment, we can say, what angle, theta, should this car have in order to, even though this is icy, an icy road, have no necessary force or slippage either in the outward or the inward direction. Remember again, this is a car going around with a radius r. It's going to have a tangential velocity v. But now we have two different forces in place, so it makes it a very good problem as an example. First of all, we have the force of gravity. Force of gravity pushes straight down, and it's m times g. Mass of the car times gravity. And that force can be resolved into two forces. One force that tends to want to pull the car down, if it were sitting on ice, to pull it down the inclined plane to the inside. If this is angle theta, then this is the opposite side, so this would be mg times sine theta. This side, the weight of the car pushing down on the road, is going to be mg times cosine theta. If you need to see that triangle again, you can kind of flip it over and see if this is the angle theta and the hypotenuse is mg, the total force that's in the vertical direction. You can see that that would give you these two components. Now we have additionally the centripetal force. The centripetal force always goes outward. Since it goes outward, there are two components to it. It would have one component in the downward direction and another component in the outward direction. If this is angle theta, what would this angle here be? Well, if this collapses down flatter and flatter, this will collapse down flatter and flatter. So this will approach zero. And so it's easy to see that this will be angle theta also. Let's see if I'm correct there. No. Let's see. Let me redraw that. Okay, this is mg, because the diagram is kind of confusing. Mg sine theta. This is mg cosine theta. This direction. And now we have the object out here that's pushed in the outward direction. And if we think about this outward direction and this vertical direction being at a 90-degree angle, and if this angle is theta over here, then this angle will be theta here. You can see that because as this collapses, this will collapse also, giving an angle theta there. And that's why we get our mg cosine theta, mg sine theta. Now we have a right angle, this going in this direction, inclined plane is at this angle theta, equivalently this angle theta. And what we want to know is, what are the components of this force either toward and out from this? Well, as you can see, as this collapses more and more, this angle gets larger and larger, and this angle gets smaller. So this is the angle theta. This theta here should refer to this angle here. And therefore, if this is the centripetal force, which is going to be mv squared over r, then if this is the angle theta, this would be the opposite side, and this would be the adjacent side. So this would be mv squared over r times cosine theta, because the theta is right here. And this would be mv squared over r times sine theta. So writing those together, we can see that we have a downward force of mg cosine theta and another downward force from the centripetal of mv squared over r sine theta. So the total downward force of the two is going to be, this is a force against the road, would be the mg cosine theta plus mv squared over r times sine, times this opposite side here, which is the sine of theta. And now we have two opposing forces, one that tries to make the car slide down the hill, the other one which tries to make the car slide up the hill. And what we would like to do is we would like to balance those two forces. And so we can say force parallel to road is going to be equal to, this is the force against the road or perpendicular to the road. This is going to be equal to mg sine theta, that's this force right here of gravity, minus this force here that's pushing outward, which would be mv squared over r cosine theta. Now, what we would like is we would like for this force parallel to the road to be such that even if you were on ice or a wet road, it wouldn't have a tendency to slide either inward or outward. So what we want is we want this to be equal to 0. We want this force parallel. That would mean that this is equal to this, or we could say nice slope is mg sine theta is equal to, or minus this would be equal to 0, so I can move it to the other side of the equation, is equal to mv squared over r cosine theta. Well, now it's neat to note, it's very important, that the mass cancels from this equation. That would mean if you worked this problem for a small car or a heavy car or a huge truck, it wouldn't matter what the mass was. And now if I take this cosine and divide it into here, I would get sine theta over cosine theta, which we recognize as the tangent of theta. And that would be equal to v squared over r times g. I brought the g through, we've got a sine theta here, the cosine theta is over there, and this is the result that I get. A very neat equation that says that the theta, the angle of the road, should be the inverse tangent of v squared over r times g. And incidentally, you can check your units very rapidly, and you can see this is a velocity squared. An acceleration is going to be a distance divided by a time squared times a distance, again gives us a velocity squared. So this side is dimensionless, as you always have to have with transcendental functions. Whether it's the result of the answer, like the tangent or the sine has to be dimensionless, or the angle itself has to be dimensionless, although given in radians. So that will give us our angle. If we want to write that out, we would say theta is equal to the tangent inverse of v squared over rg. So this is our result from this. It says if we're on a road that has ice or water, we will not slide if the road is angled, so that with our velocity and with the radius of the road and with g given as 9.8 or 10, then if the road is sloped at that angle, we have no trouble. That's a very useful calculation because it helps us in learning how to resolve these forces. You should work that problem by starting from scratch and see if you can generate that same result. Force against the road is this interesting expression here. And if you didn't have exactly that angle, this force against the road would do what? let's call that force against the road, then the force against the road is equal to the force normal or perpendicular. And that's the one that would give us our force of friction. A frictional force, you recall, is mu. That would be the coefficient of friction of the tires times force perpendicular, which would be this. Where's the sum of the two forces? Ah, here it is. Force against the road here. The sum of both mg cosine theta and mv squared over r times sine theta. So it's the sum of these two that gives us our perpendicular force, multiply it by mu, and it would give us our frictional force. If the theta that we had did not exactly balance it, our friction would have to compensate for that.